Okay, so now we're gonna go over the Coriolis effect, which is a pretty cool phenomenon. So basically, as I had said before, the Coriolis effect is responsible for causing the direction of the winds that we see at different latitudes of the Earth. So it's caused by the rotation of the Earth. So it's going to differ from the northern hemisphere is going to differ and be completely opposite to the southern hemisphere. So it causes basically a deflection of the wind towards the right on the northern hemisphere due to the rotation of the Earth, and a deflection to the left in the southern hemisphere, again due to the rotation of the Earth. So as you're seeing here in this diagram, the rotation is going to go, I guess, in a, what is this, counterclockwise direction if you're looking at it from the north, and then it's going to go in a clockwise direction if you're looking at it from the south. So with that in mind, any kind of one straight shot that you were to take from the North Pole down to the equator, because of that counterclockwise rotation, would actually be deflected towards the right. And if you think about the same kind of scenario, but in a clockwise direction, if you were to take a straight shot from the South Pole towards the equator, with the clockwise direction, the deflection would be towards the left. Okay? So again, that Coriolis effect is going to be the cause for the westerly winds that we see in the low mid latitudes to the mid high latitudes, and is going to be responsible for the easterly winds from the equator to the low mid latitudes, and also from the high mid latitudes to the poles. Okay, so again, I told you that for the most part, air is gonna, or pressures are gonna flow from low to high. That is true. If you look at, let's see, if you look at this graph, it's going to be true. It's going to rise up in the low pressure systems, and then it's going to flow towards the high pressure systems. But near the surface is going to be the opposite. It's going to flow from the high pressure systems towards the low pressure systems near the surface. So we have kind of like a rotation cell undergoing. So having that in mind, let's go back to our Coriolis effect. And in this case, nearer to the surface, those air masses are going to flow from high to low pressures near the surface, right? And with the deflection to the left or the right, then you have the wind directions occurring. So again, I said that we had easterly winds from the equator to the mid to low latitudes, right? So if you think about it in this case, the 30 degrees latitudes, those are going to be the high pressure points. So overall, my pressures are going towards the equator on both cases, which are the dashed lines. And because of the rotation of the Earth, those wind directions are deflected towards the right in the northern hemisphere and towards the left in the southern hemisphere, which in turn causes the winds to be easterly overall, as you're seeing in this little diagram. Okay? The opposite is happening for the mid-low latitudes to the mid-high latitudes. So again, high pressure system is at the 30 degrees latitudes, and then we have another low pressure system at the 60 degree latitudes. So what happens is that you flow from high to low in terms of near the surface. Winds are going to flow that way and that way. And because again of the rotation of the Earth is going to deflect those winds a little bit to the right on the northern hemisphere and a little bit to the left on the southern hemisphere, causing those westerly winds between the 30 degree and 60 degree latitudes, which is where we see those jet streams, right? Which is where we see the subtropical polar and the polar jet stream, pretty much encasing those two latitudes that I just talked about. So again, this is a little bit weird and a little bit hard to comprehend, so if you need extra time reading through that part of the chapter, I highly encourage it, and I'm happy to talk to you about it if you need extra help, so just let me know, okay? Alright, so now we're going to go over this concept of atmospheric stability, so unstable air. So atmospheric stability is basically the tendency of a parcel of air to remain in place or change its vertical position. So it wants to remain in place or change. So it's going to be stable if it stays in place overall, and it's going to be unstable if it doesn't. So you can think of a parcel of air as being a random volume of air, basically. So just taking, say, 1 meter cubed, that's going to be your parcel of air, or 1 foot cubed, or something like that. So an air mass, again, is going to be stable if the specific parcels of air within it resist the vertical movement. Or if they do move, they return to their original position after they have moved slightly. And then the air masses are considered to be unstable if those same parcels within it are rising and rising and rising, again, not resisting that vertical movement. And then as they rise, they reach air that is similar in temperature and density as the specific air parcel. Okay? So again, it becomes unstable when lighter or moist air is overlain by denser cold or dry air. So because of the difference in temperature and in moisture, what tends to happen is that you're going to get the warmer part or warmer air parcels to flow upwards and upwards and upwards until they basically become just as dry and as cold as the overlying air parcels on top. Okay, so as you're seeing kind of in the diagram, the stable air parcels are going to be these ones that tend to resist the upward vertical movement, and then unstable ones are going to be the ones that are rising all the way upwards. Okay, so when you have unstable conditions is when you start to get that cumulonimbus cloud formation and also thunderstorms and tornadoes to develop as a cause of that. Okay? Okay, so I hope that made sense. Again, these are all concepts that are kind of together. So if you're not getting something, you just stop, check your book, ask me, and move from there. And now we're going to talk a little bit about fronts. So a front is going to be a boundary between a cooler and a warmer air mass. So you may have heard about cold fronts and warm fronts, which are the two most typical ones, but we have two other ones which we'll go over later. So a cold front happens when cold air moves into warm air, as you might have expected. And the opposite is going to happen for warm front. Warmer air is moving into colder air. So so in either one of those situations, the warmer air is going to always be lifted by the colder air. Okay, so if the specific place where you were at had warm air and a cold front comes, that warmer air where you were at is going to rise. But if you're getting a warm front, then you're surrounded by cold air, and then the warm air is going to, although it's not going to impact us as highly because it's still going to be on top of that cold air. It's still going to be rising on top of it. Okay? So warm air will always be lifted by the cold, dense air mass, regardless of the front. Heat will always rise. Okay? Okay, so as you're seeing in the image below, though, the cold fronts usually causes very heavy precipitation and tends to be pretty violent, if you would. So it causes that precipitation as the warmer air is being lifted, and then it condensates in that cumulonimbus type of cloud formation as you're seeing over here. And what you're seeing over here is going to be that tropopause limit right there, right? And then for the warm front, as you're seeing in the picture, it tends to be a lot more gentle. So you do get precipitation, but it's not as, localized. It's a little bit more scattered and spread throughout. So the two other types of fronts that we get are kind of like a combination. So there's the stationary front, in which no movement of cold or air or a warm, front relationship. So there's no change within them, basically. So it's gonna have basically, as the name says, is gonna be a stationary front. Nothing is really happening. You do have two differences in the air masses, but there is no rising of the warmer air necessarily in a way that the wind is carrying it, so it's just stationary. And this happens a lot of like air stagnations. And then the fourth type of front is occluded front. So that happens when cold air fronts cold air fronts over a cold air mass is enveloping a warm air mass in between them. So it's kind of hard, and I should have included an image for you to check it out. but I think your book has one. So it's basically two air masses. One of them is going to be on top, and then one of them is going to be on the bottom. So that cold air front on the bottom is basically displacing the warmer air that used to be at the surface. So if you think about the left image, it's basically the same image, but with a colder air on top of here, and hence you end up kind of enveloping the warmer air in between the two air masses overall. So that's an occluded front. Okay? So I think you are asked in your quiz about the four fronts, but again, the most common two are definitely the cold and the warm fronts. We're going to cover the actual severe weather types of this chapter. So that's going to be called hazardous weather and geographic regions that are at risk. So the first thing we're going to cover are thunderstorms. So as you might know, most thunderstorms happen in equatorial regions or near the tropics because they tend to have more moisture about them, and that's how you get, for the most part, thunderstorms. So they are most common in the afternoon and evening hours of spring and summer seasons. Okay. For example, some of the cities that get or areas that get the most precipitation and thunderstorms in Kampala in Uganda, they say that there are thunderstorms 7 out of every 10 days of the year, which is crazy. Talking more specifically to something that relates to us in North America, Florida gets the most amount of thunderstorms, right? And then after Florida goes Georgia, Alabama, Mississippi, Louisiana, and then a little bit in the stretch of New Mexico and Colorado in the Rockies. So most of those states that I read off, except maybe New Mexico and Colorado, have a lot of moisture associated with them, as well as being closer to the tropics. New Mexico and Colorado get a lot of thunderstorms due to the high elevation at which they are exposed. So there are different regimes there, and perhaps a little bit due to wind patterns as well. And we'll go through this. In order for thunderstorms to occur, however, you need three main things. The first one is that there needs to be warm, humid air in the lower atmosphere. So this warm, humid air needs to feed the clouds, and then precipitation, like the clouds that will later precipitate and provide the energy for the storm as it continues to develop. The second thing that it needs a steep vertical temperature gradient. So the steep temperature gradient must exist in the environment. In that way, the rising air is warmer than the air that it is moving through. Okay, so that steep gradient makes the warmer air that was below to steeply rise and fastly go upwards. And again, the surrounding air is now going to be colder. Okay, and then the third thing that it needs is an updraft that must force the moist air up to cooler levels of the atmosphere. So that's pretty much what we have been talking about lately. So if you think about those three conditions, you can think about those three conditions being met for cold fronts, right? So as we saw in this slide, if you think of those three things, again, warm, humid air in lower atmosphere, check. A steep vertical gradient, check, and then an updraft that forces that moist air in the colder levels of the atmosphere because of the cold front, check. So a cold front is a perfect scenario where you get thunderstorms. Okay?